We already talked about probability, so I'm going to be talking about these two things. So the basic phylogenetic model, we talked about a tree with branch lengths. I'm going to be talking a lot about the mechanism of character change, and then I'm going to talk about the mechanics of calculating the likelihood. And this is the beast we're going to be talking about. You probably you may recognize this as what you would see like a text file that holds your data. In this case, an alignment of DNA sequences. This is the Nexus file format, which is widely used by many programs, including RevBayes, for input of alignments. I believe RevBayes can also take in FASTA and file formats as well. I know it can, in fact, because Nexus class library is used. But the basic idea here is we're treating this alignment as an observation, and we should really say, in quotes, observation, okay? Because you don't ever directly observe an alignment, would we agree? It's not like you see that out in nature. The alignment is itself a result of an inference procedure. You take your individual sequences and you run them through an alignment program, right? That's trying to establish the fine scale homology of the nucleotides for these sequences. You're assuming that you have homologous sequences, orthologous sequences to begin with, and then the program kind of establishes the fine scale homology. And what we're really interested in is the idea that this first column in the alignment, which we call a site, S-I-T-E, is that site is homologous. That is to say, we could go back in time and find a first position in the sequence that might not have been an A, but it had a first position that was directly gave rise to these first positions. We want to calculate the probability of this entire alignment, and the first thing we do is we go back to that independence statement I made. Remember, I told you that you can calculate the joint. If the events are independent, we can calculate the joint probability of the events by taking the product of their marginal probabilities. Right? That is true if they're independent. So what we're going to do is we're going to say, assert that the evolution in these different columns is independent, which would allow us to calculate the joint probability as the probability of each of these columns. So the first thing we do in phylogenetics is calculate the probability of each column, each site, on its own, and then we multiply those probabilities together to get the probability of the entire alignment. And the only way we can do that is by asserting independence. Right? It doesn't mean it really is independent. In fact, it almost certainly isn't. But that's the first big secret. Okay? So you should not feel super comfortable, but at least you understand. And so what we're going to imagine is, so that kind of pushes the problem back a little bit. Sure, now we know we can calculate the joint probability of this entire alignment by calculating the probabilities of the columns and multiplying them together. But we still need to figure out how to calculate the probability of each column. And that's the hard part. So the rest of a good hour is going to be spent on how to calculate the probability of a column. And the one thing we do know is that we want to account for all the different possible ways that we could have observed that column. So let's imagine we have this tree that I drew out, and that the column, that we only have 3 species, and this is what we see in this particular column or this site in the alignment, A, C, A. Species 1 has an A, species 2 has a C, species 3 has an A at that one column. With me? Column by column, site by site. Well, one possible history of change that could have given rise to that observation, that column, is to have a change from A to C along this branch, right? This is what I call a character history. Well, many people call that a character history, but including me, okay? Here's another character history that could explain these observations, a single change along this branch from A to C. I call this character history these different character histories, even though they involve a change on the same branch, because the change occurred at different times different points on that branch. 2 different character histories, okay? Here's another character history that could explain the observations. We have a C at the root, and then no change along this branch, no change along this branch, which would lead to a C. If we had a change at this point from C to A, we'd have an A here. And then this branch, I put a pretty complicated sequence of events, C to T, T to C, C to A. But the important point is this character history would lead to the observations we made. True? And here's another one that involves 2 changes, another one involves 2 changes. But the point is that we could play this game forever, coming up with sequences of events, different character histories that would be consistent with the observations A, C, and A. There's an infinite number of them, right? There are character histories that involve 100,000 changes along the tree, but that eventually lead to an A, C, and A at the tips of the tree. True? Okay. Now there is a method out there that puts all of its money on one class of character histories, those involving the minimum number of changes, right? So what it does is, for a particular tree, it goes across all the different columns and calculates the minimum number of changes and takes that sum as the proxy for how good the tree is. That's called the parsimony method. There, you have the parsimony method. But the point here is the parsimony method puts its money down on character histories that involve the minimum number of changes for a particular tree. Likelihood, distance, Bayesian methods, they spread their bets out over all the possible character histories. Especially maximum likelihood and Bayesian methods do it very explicitly. But when you calculate a likelihood, you're not assuming any possible character history. You're assuming all of them. The probability accounts for all the possible histories, weighting each character history by its probability under the model. Okay, that's the important point. But the important point is that likelihood, when we calculate a likelihood in a Bayesian analysis, it marginalizes over all the character histories. Remembering the marginalization technique where you sum probabilities over all different possible ways you could have gotten some event occurring. We're marginalizing. And of course, the big question is how do we, that seems like a complicated thing to do. How do we do that? And it is complicated. What else did I want to say here? Oh, one other point I wanted to make. It's very tempting to call these tick marks mutations. Oh, we had a mutation from A to C along this branch. Don't do that. Okay, don't call them mutations unless maybe it's a coalescence tree. Call them substitutions. When we have different species at the tips of the tree, species 1, species 2, and species 3, we think about a process where a mutation became fixed in the species or the population. So a substitution is a mutation that eventually became fixed. Mutations occur, they land on a chromosome in some individual. A substitution is a mutation that eventually spread through the population, right? So we're thinking about typically fixed differences or almost fixed differences between species. So call them substitutions. Boris, you have a problem with that? No, I'm enlightened by it. Okay, but it's okay, good. It's important because some of the, just making certain I didn't miss anything. So I don't have a problem with the guys whispering each other, but I was thinking, shit, did I say something wrong? So, but fortunately I didn't think I did. Or that if you wanted anything added. But it does come up for, the fact that these are substitutions is important because when we talk about codon models, this is where all the fun starts, right? Because population genetics theory makes certain predictions about what the substitution rate should be, right? If they're neutral changes, Kimura said that the substitution rate should be equal to the mutation rate. And so we can often think of, if we can find a class of changes that we think are neutral, that acts as a scale that we can measure other types of changes against to determine whether they're being selected. Okay, so that's kind of a key to a lot of the non-synonymous, synonymous business you'll hear about. Okay, so so that's our goal. We want to calculate the probability of a column while at the same time marginalizing over all the possible character histories that could occur. This is the way we do it. So this is a different situation, 3 species again, but the observations we made in the column now, instead of being ACA, are GG and A. Different column, same alignment, okay? So we're looking at just the column, and it's GGA. And for right now, I'm assuming that we know the ancestor is A. We know the ancestor at this point in the tree had an A, and the ancestor at this point in the tree had an A, and that we have these branch lengths. Remember the product of time and substitution rate? Here, V1, V2, V3, and V4. Those are the expected number of changes along each of those branches. Ignore for the time being that we can't look back in time and figure out that we had an A and an A here. Just ignore that for right now. But if we could know that, we could calculate this probability very simply. We would have this factor pi A, which is the probability of the A at the root of the tree. Whenever you see a pi in these calculations, it's the probability at the start of the process or at the root of the tree, times the probability of ending in an A, conditioned on starting in an A over a branch of length V1. That's this. This is called the transition probability from A to A over a branch of length V1, but it's really a conditional probability. Conditioned on starting on an A, what's the probability of ending in an A? Times the probability, transition probability AA over a branch of length V2, the probability of ending in an A, conditioned on starting in an A over a branch of length V2, times the probability of this little segment of the tree, times the probability of this little part of the tree. So you have these different factors that account for the changes that occur along the different branches. And I guess there is an implicit assumption of independence here because we're multiplying probabilities together. What that means is that we think a change along this lineage, along the species that was in existence at this time, that any changes at this site are independent of changes that occurred at the same site in this other lineage. Unlike the first statement of independence I made, where we're assuming that the substitutions are independent in different columns of the alignment, I feel pretty comfortable with this one, right? I think most people do. So this is not a controversial statement of independence, but the first one I made, I think, is. These different factors have different names. The pi is called the stationary frequencies or stationary probabilities, sometimes prior probabilities of the nucleotides. And these other bits are called the transition probabilities. And what I want to talk about now is how we calculate these things. But before we do that, I want to get rid of the first stupid thing I said, which is that we're going to assume that we have an A here and an A here. So how do we calculate the probability if we don't want to assume a specific combination of nucleotides at the ancestral points in that tree? Well, we do the usual thing. We marginalize, right? So we marginalize over all the possible combinations of nucleotide assignments that we can make to the interior parts of the tree. So note the tips are always GG and A. We saw those. But here we have AA, AC, AG, AT, and so forth. There's going to be 4 possibilities at each node. So that's why we have 16 things we're summing over. Okay? Make sense? We marginalize over all the different assignments of nucleotides at then interior parts of the tree, interior nodes of the tree. Now, a very simple thought experiment will show you that we can't be doing this in real life, right? Explicitly this. So, if we have 3 tips, then there's 2 interior nodes and 4 times 4, or 16 possible combinations, right? And if we had 4 tips, then we would have a 4th species, and it would join here. We'd have 1, 2, and we have 3 interior nodes. We have 4 times 4 times 4, or 64 possible combinations, right? Well, what would happen if we had, basically the rule is you have 1 fewer interior node than you have tips, at least for rooted trees. So if we had 100 species, we'd have 99 interior nodes, and we'd have 4 to the 99th, I don't know what that is, but it's a big number, possible combinations, like 10 to the 50 or 60 or something like that. So that sum is too big for a computer to handle. I mean, you could start it up and say, it's something you could program, certainly, but it would be cranking, and just to calculate the probability of that one sum would take to the end of time practically. The sun would explode or something, and you still wouldn't be done. It turns out that there's an algorithm that does mathematically the equivalent thing, okay? And it relies on this idea that if you look at this little part of the tree where we have GG and we have an A here, note that all 4 of these trees at the top have that situation. They have the GGA, 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 right? And similarly, here we have GG with a C here, right? It's basically, if we were to think about the probability of this little part of the tree, it's going to be the same here, 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 and here, right? So there's an algorithm that Felsenstein first described in 1981 that takes advantage of these patterns that are repeated. So basically, I've heard Paul Lewis describe it most eloquently. You're trading off, you're trading memory for speed. So if you could remember those numbers, store them in computer memory, and we have plenty of memory these days, then you can speed up the algorithm considerably. And that's exactly what the Felsenstein pruning algorithm does. This is the reference, very famous, very highly cited paper, Evolutionary Trees from DNA Sequences, a maximum likelihood approach. And in that paper, he describes in the evolutionary biology literature what we now term the Felsenstein pruning algorithm. Now, the graphical model, you guys have already been introduced now to graphical models. We did the baby graphical model earlier. That literature goes back decades and decades. And so that same algorithm was described in the graphical models literature 2 decades before by this guy Gallagher. So if you were to talk to somebody who's a computer scientist who uses graphical models a lot, they would call that not the Felsenstein pruning algorithm, but rather the sum product algorithm, because it takes sums of products. Okay? Products of sums, rather. Okay, that's what it does. Oh, anyway, so how does this algorithm work? Well, what we imagine is that every part of the tree we're going to remember 4 different numbers. Okay? This is the probability of A, C, G, and T. I always alphabetize alphabetically order my nucleotides. So A, C, G, T. These are called conditional probabilities. The probability of the observations above that point in the tree conditioned on having an A here, conditioned on having a C, G, or T. So we have that for the tips, but we also have it for the interior parts of the tree. So this is the probability of the data above this point in the tree, which includes all of this that I'm circling, conditioned on having an A here. Okay? That would be kind of equivalent to the previous part where I said that would be where you put the number that would account for this top part, this little probability right there, conditioned on having an A. And then down here, you have the probability of all the observations, above this point in the tree, conditioned on having an A at the root of the tree, A, C, G, or T. So that's what we're going to, we're going to be remembering these probabilities. Now the first step is you initialize the probabilities, the conditional probabilities or conditional likelihoods at the tips of the tree. So if you see a G, then you put a 1 in the G box and 0 in the others. If you see an A, you put a 1 in the A box and 0s in the others. That is to say, the probability of seeing a G here, conditioned on there being an A here, is 0. It's a nonsensical statement, right? Probability of there being a G here, conditioned on there being a C here, is 0. Okay? But the question is then, how do we fill in these probabilities lower down in the tree? It's easy to fill in the tip probabilities, but what do we do lower down in the tree? Well, this is what we do. We traverse the tree, starting from the tips, which you really only have to visit once to initialize these probabilities and never change. But then we go down the tree visiting nodes in a specific order, called a post-order traversal of the tree, in such a way that every time we visit a node, we've already visited the nodes above it, right? So we're going to visit this node first and use the information here and here to calculate the probabilities here, and then we're going to visit this node and use the probabilities we calculated here and here to fill in these 4 numbers. Okay, so we're going to traverse the tree in a specific order. Each time we visit an interior node, it's kind of like this. You're sitting here, right, and you're looking up, right? And you look up, and to the left you see a branch that has a length of VL, and you look up to the right and you see another branch that has a length of VR. And then you see 4 numbers. These are numbers, they're not blanks. They're actually 4 numbers here, and there's 4 numbers here, okay? And you want to fill in the number, say, here. So this would be, this here is the number, this symbol here is the number we want to fill in here. So this might be, I might be an A, in which case you're filling in this box. I might be a C, in which case you're filling in this box, or a G, or a T, right? So you're going to go through this 4 times, calculating the probability here by doing this thing. So if I is an A, then what we're going to do is we're going to sum over the 4 nucleotides up here, calculating this. This is the transition probability from I to J, A to C, A to G, A to T over this branch, times the probability of the number that's here. All right? This L is not raised to the power of, it's just telling you it's the number that's written in the box to the left. Okay? And you do the same thing, summing over these 4 possibilities for the probability, the numbers that are written in the right and the transition probability to the right. Okay? So this, if you ever wonder why maximal likelihood and Bayesian inference take a long time, almost all the time in these programs is spent doing this stuff. These products, this product and these sums. Okay? Sum product algorithm. Oh, so this is what you're doing. You hit each one of these, you sum over the 4, you hit this one, you sum over the 4 nucleotides. The sum was when you're dotted going over this. So let's go ahead and see what this looks like for the entire tree. First of all, you can initialize the probabilities of the tips. Then we visit this node, doing the sums over the different nucleotides here, filling each of these 4 boxes independently. Then we can do these. And once we've got these 2 boxes, we can visit down here once we've finished filling in these. Now we can fill in these 4 boxes, given the information here and here. Now the important point is this. When we have the number finally filled in here, this is the probability of all the observations, but conditioned on having an A here. We don't want a condition on having any particular state at the root of the tree. So we average over the 4 marginalize, over the 4 possibilities. So it's going to be the probability of the A here times the prior probability, or the stationary probability of having an A, plus the number that's written here times the prior probability of having a C here, and so forth. So we do this average, calculate this average probability at the root of the tree. That is the probability of a column, okay, that we use. Now, you'll note that we use 2 things you saw earlier. We have the stationary probabilities. Those come in, once again, when you're calculating probabilities at the root of the tree. We also saw we had those transition probabilities that I showed you earlier, the PIJs. I still haven't told you anything about how you get those. We're using them willy-nilly, but I never explained them to you. So that's what I'm going to do next. Oh, right, that's kind of fancy. All right, that probably took me longer than I wanted. Oh, before I move on, because this might come up later in the lecture, what do you do if you have ambiguity? So I told you what to do if you saw a G at the tip. You put a 1 in the G box. But what if you had a C or a T? Right, what do you put then? Well, then you put a 1 in the two boxes that correspond to a C or a T. Not a half, but a 1. Why is that? Because the probability of a C or a T, if there was a C here, is 1, right? That's why. If you had a question mark, then you put a 1 that is totally ambiguous. You put a 1 in each of those 4 boxes. And an important note is almost all these programs, Mr. Bayes, RevBayes, Beast, Pop, Star, Garley, Braxamel, they treat gaps, insertions, or deletion events in your sequence as question marks. So formally what they're doing is they're putting 1s in all those boxes. It's not a fifth state or anything like that. It's treating it as ambiguous. All right, so to remind you, there are 2 things. I mean, the Felsenstein pruning algorithm that I just showed you basically removes, it's a very fast way of calculating all the possible combinations of nucleotides that could be at the interior nodes of the tree. That's what it's really accomplishing. What I want to do now is talk about how, where do these transition probabilities, which were used in the Felsenstein pruning algorithm, and the stationary probabilities, where do they come from? How do we calculate them?
Another question.
Yes?
The branch length, when you're calculating the likelihood of a site, you're throwing branch lengths to get the likelihood.
Yes.
Right? And the branch lengths come from the remaining sites, I imagine.
No. So the branch lengths come from somewhere, right? They don't come from necessarily the other sites. They're a number that you've chosen, all right? Now the computer program, where do so it is a good question, like where do those branch lengths come from? But let's say we're doing maximum likelihood. Well, where the branch length would come from is to say, the program would be saying, okay, I need to find the combination of branch lengths that maximizes the likelihood. And in the course of doing that, it's going to try all different, it's going to try different branch lengths to see what the likelihoods are to determine which are better than others. Now, as an aside, there's very efficient ways you can do that, but the point is, it's going to say, well, shoot, I think another good guess for the branch lengths would be this. And it gives these very specific numbers, and then it would calculate the likelihood under those numbers and compare them to likelihoods it calculated earlier with other branch lengths, right? So that would be in the course of trying to find the maximum, the combination of branch lengths that maximizes the probability. They don't come, I mean, in a sense that all the sites contribute to the probability, but the point is that whenever you're calculating the probability, there are always specific numbers there, right? And so Mr. Bayes or RevBayes or Beast, the branch lengths would come from the Markov chain Monte Carlo algorithm. It would be proposing a new tree, and that tree would have branch lengths on it, calculate the probability of the data under that proposed tree and branch length combination and compare it to previously calculated values. So over time, I think what you're, I kind of know where you're coming from. I think what you're confused about is like, isn't that circular? Well, the point is you want some circularity because you want your data to affect your branch lengths, right? You want them to be associated, right? You want branch lengths that are going to explain the data well, and some will, and some will explain the data more poorly. But where they come from it's not like you look at the other sites and determine how we're going to calculate the branch length for the tree. All of the sites share the same branch length, and that branch length came from an algorithm that's either in the process of maximizing the likelihood or trying to calculate the probability distribution of the tree and branch lengths or something like that. Okay. I think that answers the question, like where I think you were coming from. All right, but to go back, just to remind us, we want to know where these stationary frequencies and transition probabilities come from and what they mean, right? Well, it turns out that they come from calculations we make under what's called a continuous time Markov model or Markov chain. So continuous time, because we're going to be in phylogenetics measuring time on a continuous scale, not in terms of like discrete generations or anything like that. It's a continuous scale. And it's a Markov chain or Markov process because the next state of the process depends only on the current state. You don't need to know anything about its ancient history to figure out where it's going to go next, what the probability of it going to different places next. And this is an important point. You might be reading the literature on these phylogenetic models going forward, and I'm sure you've probably read some in the past. And the literature is full of complicated models. You've probably heard of models like the Codon models or Doublet Models or different, the MK model. It turns out that all of the models in phylogenetics are continuous time Markov models. They all come down to one case. And I'm going to give you one example of a continuous time Markov model to illustrate the point. But when you're reading these papers, try to laser in on two things. What are the states of the process? Right? In this case, I'm going to be talking about a case where we have 4 states, which are the nucleotides, A, C, G, and T. So this model has 4 states, but other models might have more. But try to figure out what are the states and what are the rates of change among all pairs. If you know those two things, you know everything about the model, in a sense. Right? So here, I've put 12 arrows. This arrow here is the rate of change from G to A, and this other arrow that's right next to it is the rate of change from A to G. Here's an arrow that's from G to C. This arrow here, which is right next to it, is the rate of change from C to G. So there's 12 arrows if you count them all up. The 12 pairs of nucleotides, the 12 rates. So I'm going to claim that if you know both of those things, the states and the rates, you're good to go. Now there's a way of summarizing these rates in a table, and here's an example. So you could also take those 12 arrows and put them into a table. Now, once again, in order to calculate probabilities, the computer has to have in computer memory specific values for all those arrows. Right? There are real numbers in computer memory that you could read off in principle that would be the values for each of those 12 arrows. And here's an example that we're going to use over and over where I give specific examples. For instance, the rate of change from C to A is 0.253. Right? Where did I get that number? Don't worry. I just chose it. Right? But that's what I'm going to say the rate of change from C to A is. And the rate of going from A to C is 0.19. This would be the arrow right next to this arrow. So if you look at this table, there's 12 numbers that are positive, that are off diagonal parts. Those are the numbers that correspond to the 12 arrows I showed you on the previous slide. Okay? And then you'll see that there's 4 additional numbers here which are negative that I put here. A way of interpreting, or the way to interpret these numbers, is they're the rate of change away from that nucleotide. Right? So for instance, if we have a rate of change from A to C, A to G, A to T, then this is the rate of change at which we're going from A. It's going to be the sum of this number, and this number, but the negative of it. So if you check this, 0.886 is equal to 0.19 plus 0.633 plus 0.063. Right? If you kind of ignore that negative sign, 0.886 equals the sum of those 3 numbers. So what we do is we specify each row such that the sum is 0. That puts the negative number here. But a way of interpreting this is the rate of change away from the nucleotide. But the important point to know is that this sum, this negative number, is completely determined by the 3 numbers that are positive and not on the diagonal. With me? So I tell you this number, I tell you this number, I tell you this number, and then you can tell me that number, what it has to be. It's not like it's an independently chosen number. It depends on what those numbers are. And they're chosen such that each row sums to 0. So this is a table of the rates. And if you go to the literature, you'll never hear the term rate table. Well, here is the rate matrix. Right? So here's the same table, but in matrix form. Right? So I'll go back and forth. Oops. There's the table. There's the matrix. Okay? With me? Same thing. Nothing different. But it looks more complicated, or at least it sounds more sophisticated. So if you want to sound sophisticated, never say rate table, because people just laugh at you. Say rate matrix. People think you're cool. All right? But it's the same numbers in matrix format, and typically people use the terminology Q to represent that entire matrix of rates. Okay, so this is the key point. How do we interpret that rate matrix? Well, we interpret it as rates. And so the interpretation is this. If the process is in state I, we wait an exponentially distributed amount of time with parameter minus qi until the next substitution occurs. What does that mean? Let's imagine that the process of this model is currently in state t. Well, it says we're going to wait an exponentially distributed amount of time until the next substitution occurs, and the rate of that exponential is going to be read from the element qtt, which is this one. This is the qtt, t right there, and you take the negative of this number. This is negative 1.329, so that makes it 1.329. So the rate is 1.329 when we're in t. Okay, and exponentials, well, I'll tell you what exponentials are. But before I do that, there's one other additional thing this rate matrix tells you. It says that when there is a change, you can read the probability that it's a change from t to A, t to C, or t to G directly from the rate matrix. So it says the change, when it occurs, is to state j with probability minus qij divided by qii. So what does that mean? Well, again, if we're at t, the probability it's a change from t to a is 0.253. That would be this part, divided by the overall rate of change, 1.329. Right? The probability to t to c is 0.949 divided by that number, and so forth. So it tells you two things. It tells you how long you wait. It doesn't tell you exactly. It's a probability distribution, but it tells you the parameter of the exponential for how long you wait. And then when you have a change, it tells you the probabilities to the different possible states. So a little bit about exponentials. So we're imagining a situation like this where we start observing a process at time 0 going forward, and we imagine that something, some event, so here's some examples of things you might model in this way. Maybe the arrival of a customer to a call center or a store, or coal mining disasters have often been modeled this way. What's the rate at which you have a mine collapse, some serious accident, a photon hitting a photodetector, a particle emission from a radioactive substance, or in our case, a nucleotide substitution. We're going to assume that it occurs at some rate, right? We're going to call that rate lambda typically. So, all right, yeah, lambda. So the rate at which the somethings, like nucleotide substitutions, occur is called lambda. And we imagine we start observing the process here. We saw one event there, one event there, one event there. Maybe we have 3 different coal mining disasters that occur at different times, or we have 3 different nucleotide substitutions that occurred at that site. This is the waiting time to the first event, or the sojourn time. This is the second sojourn time, the time we wait for the second event to occur from starting time from when we saw this one. And this is the third sojourn time. You see the sojourn times are just the arrival times between the events. Important fact, this is the only thing you really need to know, all right, in terms of probability distributions as far as I'm concerned. The important point is those sojourn times, those times between the events, are exponential random variables, exponentially distributed random variables. So this is what the exponential probability distribution looks like. Time start, this would be time 0, and time goes off this way into infinity. Lambda is the rate at which the things occur, substitutions occur. T is how long you wait. So this gives you the probability density to wait a certain amount of time for an event. Right? That's the only thing you need to know. Exponentially distributed random variables. Now here's some things that you can turn off, listening if you want. And so I'm just going to tie a couple of other things in here. But I just told you that the times, that this time are exponentially distributed random variables. But let's say you were sitting there and you're going to count every other event. So, here's this would be the situation where you say, okay, I'm going to not keep track of the first event, but every time it's an even number, I'm going to click my stopwatch, right? So this would be the waiting time to the second event, and then you could say, what's the waiting time to the fourth event, and so forth, or every other event. Or you could say, I'm going to record every third event, or I'm going to record every fifth event, things like that. What is the probability distribution for those? Well, it turns out that's the gamma probability distribution, which you've probably heard of. Have you heard of gamma rate variation? Right? How many people have heard of that? Okay, most of you have. So it turns out that gamma probability distribution was not invented by some statistician who says we really need to model rate variation, so here it is. Rather, this is a generalization of waiting times. It's the sum of exponential random variables. So if you wait every other event, for 2 events, it's the sum of 2 exponential random variables. If k is 10, then it's 10 exponentially distributed random, or the sum of 10 exponentially distributed random variables. If k is 1, then you're waiting just to the next event. It becomes the exponential. So the exponential is a special case of the gamma. So the gamma was not invented to model rate variation. We just stole it. Right? It has 2 parameters, lambda, which is just the rate at which the events occur, and k, which is which event you're waiting to. Here's another way of thinking about the process. Let's say you start watching the process, in the morning, maybe 8 in the morning, and you're a good graduate student. You keep watching the process to 3 or 4 in the morning. Okay, good long day. And what you're doing is just keeping track of how many events occurred. Just like how many events did I see? So you are watching the process, observing the process over capital T time. The number of events that occur in that interval are called a Poisson distributed random variable, and the parameter of the Poisson is lambda. The rate, the same rate we saw in the gamma and the exponential, and in this case, how long you observe the process. And it just tells you whether you saw 0, what's the probability that you saw 0, 1, 2, 3, and so forth, events in that interval. So the only distribution you need to know is the exponential. The waiting time to the next event is exponentially distributed, but if you've heard of the gamma, you've heard of the Poisson, this might tie it together conceptually, those probability distributions for you. So it's just FYI. Okay, so let's go back to our rate matrix case and think about how we might simulate DNA sequences. The first thing we want to do is we want to think about a branch, and we're going to think of one end, the lower part of the branch, as being the starting point for our simulation, and the top end of the branch as being the finish line. And the length of the branch is how long the race will be run, right? V, the branch length. Here's our rate matrix, right? This is just the same rate matrix I showed you earlier. And for right now, I'm going to force the process. I'm going to make the decision, the non-random decision, that I'm going to start the process in state G. I just decided I'm going to start it in G. So the rate matrix is something I chose. The length of the race, I also chose that. And I decided I'm going to start this process in G. But from here on, we can use the rate matrix and random numbers to determine what's going to happen. So first of all, if we're a G, that means we can forget every other row in this matrix, the rate matrix, and just concentrate on this row, the one I kind of highlighted. So when we're a G, the rate at which something occurs, that we have a substitution, is 1.519. We can have a G to A, G to C, or G to T change. The sum of those three rates is 1.519. With me? So we wait an exponentially distributed amount of time with parameter 1.519 until the next event occurs. There it is. Somehow I generated that exponential random number, and I determined that the next event's going to occur right there. The rate matrix also tells us the probability that when we have that changes to an A, it's going to be an A with probability 1.266 divided by 1.519. It's going to be to a C with probability 0.19 divided by the total rate. And it's going to be to a T with probability 0.063 divided by the overall rate. These three numbers have to sum to 1. They do if you check. So we choose one of these three things at random with the appropriate probability. So let's go ahead, and I happen to choose that. Right? Now we're in an A, so we can forget about the other three rows and just look at the A row. When we're in A, the overall rate of the process is 0.886, so we wait an exponentially distributed amount of time with parameter 0.886. We have another change right here. That rate matrix again tells us the probability that changes from A to C, A to G, or A to T. A to C with probability 0.19 divided by the total, 0.633 divided by the total, or 0.063 divided by the total. Get those three probabilities. Once again, another random chance. You have to make another random choice. Maybe we randomly choose this one. Now we're a C. The rate of change when we're a C is 0.696, and our next event of change occurred after the finish line. So we truncate it. We started in a G. That was not a random choice. But we had two changes, and we ended in a C. That was a random choice. Random but constrained, not like random in the sense of choosing A, C, G, and T with probability 1/4, but it was constrained by the process, right? So it was a random, it was a random variable, essentially, the result C. Yeah, I'll confess that was not really something I did randomly. That was just, I just used it for example. But I did write a computer program that really does this randomly, or pseudo, using pseudo-random numbers in computer memory. And so this is what I did. I used the same rate matrix I showed you guys, right, in the previous slides. The branch length is 0.1, and each one of these bars, vertical bars, is a result of a simulation. I always started the process in G. That was not random. So every one of these starts in G. It's red at the bottom. But for instance, this very first simulation, if you look at it, it was G the entire time. So we started in G, and then we ended in G. What that means is that our first, when the program simulated this first site, the change was greater than 0.1. It said that the waiting time that it generated, the exponential waiting time, was greater than 0.1. So the point is here is when the process passed this point right here, it was still in G. With me? This next one's kind of interesting. So it started in G, then we had a change and went from G to, I think that's T, right? I think yellow was T. It was in T for a while, and we had another change, and it changed from T to C, and it ended in C. And so we had two changes, and with the ending in C. Then we had 5 changes in a row, or 5 simulations in a row where we didn't have any changes over this interval of time. Here's one where we had a change from G to A, so we started in G and ended in A. And you see a lot of these cases where we start in G and have changes to A. Here's kind of a cool one. start in G, almost immediately change to A, right? And we're at A for a while, and then we have another change, and it's back to G, and we end in G, the same state we start with, right? And there's one other that was the coolest one. So here's one. Start in G, almost immediately change to A, and we're in A for almost the entire duration of the branch until just the very end, and we have a change back to G, right? So if you looked at just the start and end points, you'd say, well, geez, it looks like there was no change. And indeed, you could see in most of the simulations, when you had a G at the beginning and the end, there were no changes. But in a couple of cases, like this one, you would be so wrong because most of the time it was actually an A, right? Which is kind of cool. But this kind of gives you an idea, like when you're assuming these continuous time Markov models, as you are, when you're using any of these programs like PopStar, Mr. Bayes, RevBayes, RaxML, Beast, you're assuming the process looks like something like this. It's a stochastic process, right? Continuous time Markov model. So anyway, this is an example of 100 simulations with the rate matrix I was showing you guys earlier. And I want you to note something, though. You know, what was not random about this? Well, what was not random about this process was the length of the branch, because I said we're going to run every one of these simulations over a branch length 0.1. It's not like every simulation we said, oh, let's draw the branch length from a probability distribution. No, I decided everyone's going to be 0.1. And I also decided that every time I do the simulation, it's going to be starting in a G. That was not random either. And also the rate matrix. You know, can't forget about the rate matrix, which I'm not showing you, but we're assuming that rate matrix, right? But the end result, you can think about, we could not have predicted that exactly, right? We could not have said, every time I do this, we always end in a G. We couldn't say that. It ended in a G with some probability, right? And in fact, when we did these 100 simulations here, we saw that we ended in A 31 times, we ended in C once, we ended in T once, and we ended in G, the same state we started the process in, 67 times, right? That's what we did. Those probabilities, if you divide each of those numbers by the number of simulations I did, 100, you could turn those into probabilities, right? So remember, this is the probability of ending in an A, conditioned on starting it. It's a conditional probability, conditional on starting in a G over a branch of length 0.1 up here. So these are what you would call Monte Carlo simulation estimates of those transition probabilities. So remember what the transition probabilities were? We're using them in the equations when we're trying to get with the Felsenstein pruning algorithm. There were the PIJV, right? That is the transition probability. This would be a way of simulating those probabilities, okay? Now, of course, if you did 100 simulations, you might imagine these probabilities aren't very accurate. So here's the same probabilities, but with 50,000, based on 50,000 Monte Carlo simulations, right? So these should be pretty close to the exact probabilities. They're Monte Carlo estimates, so there's going to be some Monte Carlo error. But these, what this means is that the probability of ending in an A, conditional on starting in a G, is about 0.11. Okay? How would we fill in these other missing entries in this table? Yes? Exactly. So you would do the same procedure, the simulations where I always started in a G, but instead of always starting in a G, you would always start the simulation in an A if you wanted to fill out this row, always start in a C if you wanted to fill in this row, or a T for this row. In fact, this would be what you do. Here's cases where 100 simulations starting in an A, 100 starting in C, and so forth. You do simulations like that. And if you were to do that, I'll go right to the 50,000, you'd be able to fill in the other missing entries in this table. Right? Once again, these are Monte Carlo estimates of the probabilities. Imagine, what would happen if I changed, wanted to calculate these probabilities with, instead of a branch length of 0.1, 0.11. Pretty close, but not exactly the same. What would you have to do? Redo all the simulations, right? Because those probabilities, all these probabilities are assuming a branch length of 0.1. Or, let's say I change the rate matrix in some minor way. To redo the simulations, right? Because these probabilities are only valid for that, the branch length of 0.1 and the rate matrix I was showing you guys earlier. Now it turns out you don't have to use Monte Carlo simulation to calculate these transition probabilities. So here are the Monte Carlo estimates of the transition probabilities based on 50,000 simulations. 50,000 for each row. So there's 200,000 simulations total to get this. These are the exact probabilities to 4 decimal places, right? So, for instance, the transition probability AA is 0.918. That 0.918 is the Monte Carlo estimate of 0.9191. This is the exact probability, that's the estimate. So these exact probabilities can be calculated using what's called matrix exponentiation, right? You look on your calculator, there's no matrix exponentiation button there, I'm pretty sure. But what you do is you take, kind of ignoring this part, you take the rate matrix and multiply it by, well, I put T here, think branch length, V, sorry. Multiply each entry of the rate matrix by the branch length V, and then you exponentiate the rate matrix. And there's ways of doing this in computer code, right? So you don't have to worry about how that happens, but the important point is you can get these probabilities exactly, or to some precision, just a numerical method. But the important point I want to say is this: when you calculate this, when you get these transition probabilities, these probabilities account for all of the ways that the process can end in a particular state, conditional on starting in a state, right? It accounts for the infinity of ways, the infinity of character histories along a single branch. Now, importantly, when you combine the transition probabilities, the matrix exponentiation really, with the Felsenstein-Pruning algorithm, that means when you calculate the probability of a column in your alignment, that probability accounts for all the character histories that could have led to your data. That's the trick. That's how we do it. We rely on this idea that these transition probabilities, branch by branch, account for all the different possible ways you can get from this part. Do it segment by segment, branch by branch. We can calculate all the different possible ways you can end in an A or a particular state conditional on starting in a particular state. And when you combine that with the Felsenstein-Pruning algorithm, the overall probability of the data you saw at that column in your alignment accounts for all the character histories. We're spreading our bets out over all of them, which is the cool thing about likelihood calculations in my mind. You don't have to say, oh, we're only interested in the character histories that have the minimum number of changes, like a method that you all are familiar with does. We account for all of them. We spread our bets out over all of them. Okay. So just to remind you, the transition probabilities for any rate matrix Q can be calculated by matrix exponentiation. You don't have to know the details of that if you're interested in that, of course. There's like all the instructors in this class are familiar with how to do that, and we can point you to algorithms or code in the RevBayes that will allow you to do that. But the important point is you just have to realize that you can calculate the transition probabilities for any rate matrix. Now, that deals with the transition probabilities. The next thing I want to turn my attention to is the stationary frequencies. Where do those come from? Right, so I want you to say it's the same process. The continuous time Markov model also allows us to, the rate matrix also allows us to get the stationary probabilities. And what I'm going to show you here is kind of like a little psychological test. I'm going to show you 4 plots, always starting in A, always starting in C, G, or T. I'm going to show you the exact transition probability matrix, or at least to 4 decimal places. And this is the only one where I'm going to be showing you where if you look at the top, it kind of doesn't make sense. But if the branch length is 0, that is to say you have no opportunity for change. If you start in A, you always end in an A. Does that make sense? Okay, this is kind of the starting condition. This makes sense. What doesn't make sense is, I'm drawing these as if there's some amount of time, whereas this is really 0. So forget this one, but if you don't have any opportunity for change, intuitively you don't have any change, okay? But this next one makes sense. This is a branch length that's 10 times shorter than the one that I was showing the simulations for earlier, a branch length of 0.01. And you can see visually, if we were to simulate, this is 400 simulations total, you see very few changes over all 400 of them. In fact, I see 1, 2, 3, 4, 5, 6 changes. But notice the transition probabilities. If I start in an A, I almost certainly end in an A, right? If you have a very little opportunity for change, you almost always end in the same state you start with. That makes sense. Now here's the case I showed you guys earlier, branch length of 0.1. Now I'm going to show you a branch length of 0.5. Now we're looking at branch lengths 5 times longer than the ones I showed you earlier. You see visually many more changes and many more instances where we have multiple changes, like here, from blue to yellow, yellow to red. You're going to see a lot more cases where you see multiple changes. Here's yellow to green, green to yellow, and so forth. But also you can see the transition probabilities, the probability of ending in the same state you begin with becomes smaller. Okay? I want you to kind of, if you see some interesting pattern emerge, shout out or raise your hand or hiccup or something. Here's a branch length of 1. This would be considered a very long branch in the phylogenetics literature. On average, 1 change per site. Right? All right, here's a branch length of 5. Anything interesting yet, people? Yeah, well, look down here. Look. Here's a branch length of 10. Here's a branch length of 100. Here's a branch length of 1,000. You see the pattern? What we have here is, if you look at, we go back now that you sort of see the pattern, 0.4, 0.3, 0.2, 0.1. Look how we converge there. 0.1. I mean, all the values in each column get more and more similar. There, you can actually kind of see it there. Branch 5, it's like they're all starting. This is all starting to look a little bit like 0.4. This is all starting to look like 0.3, and so forth. And then here, once you get to 10, even closer. And then once we get to 100 or 1,000. So this is the point. In this particular, this was all for that rate matrix I showed you earlier, right? The rate matrix I never explained to you guys. But the idea is if we were to run that process for a very long time, like a branch length of 100, say, or 1,000 or 10,000, what happens is we're going to end in a state A with probability 0.4, regardless of which state we started in. In a sense, the process is completely forgotten its starting state, right? It doesn't matter anymore. We end in an A, we see it in an A after a very long time with probability 0.4, or C with probability 0.3, and so forth, right? So when you run the process for a very long time, it's said to reach stationarity or get very close to it. Formally speaking, you run it for infinitely long, but that would allow us to get these probabilities in the limit. But the idea here is think very long time and capturing the process in some particular state. Now, where were these stationary frequencies used? Where was that pi? Remember, these are the pi's. Where were they used in our calculations? The tip of the tree? At the root of the tree. They're always used at the root of the tree, right? Kind of, I said at one point, they kind of start off the calculations that we need. So think about it like this. Think of our trees as having, you have the common ancestor of all the species we're interested in. Then think about there being a really long tail on that tree. So we imagine the process has been running for a very long time before it gets to the part of the tree we care about, okay? And so that by the time we get to the root of the tree where we care about it, we think of the process as being at stationarity. So the probability of an A, C, G, or T at the root of the tree is drawn from the stationary distribution. Now, there's some applications where you might not want to do that. And in fact, Boris and Emma, I think, had a paper a decade ago where they pointed out in some circumstances that might be a bad thing to do. But the phylogenetic methods, that's what they're assuming. They're assuming the process is at stationarity by the time you get to the root of the tree, right? And interestingly, all we had to know is the rate matrix to do this, right? Just like the transition probabilities, all we needed to know is the length of the branch and the rate matrix. To get stationarity, or the stationary probabilities, it's like running the process for a very long time. What's the probability of capturing the process in a particular state? All you need is the rate matrix. So the cool thing about continuous time Markov models is, like I said in the beginning, if you know the states and the rate matrix, you're good to go. You can get everything you need, the transition probabilities, stationary probabilities, those other things that we don't need that you can also calculate from that, right? But all we need is the stationary probabilities and the transition probabilities, those two things. Kind of interesting, if I were to show you any one of these 4 plots, like if I showed you this one, but out of context and said, what was the starting state, right? You would have a hard time telling, right? Unless you could get like a magnifying glass and look down here, right? So the cool thing is that you really would have a hard time distinguishing which what the starting state was for any one of these once you kind of get at stationarity. Okay, so the stationary probabilities, and they have some other names that they're often used in the literature. The probabilities of finding the process in some state after an infinite amount of time, and they're typically, the symbols we typically use are A, C, G, and T, and for the rate matrix I was showing you guys earlier, they happen to be 0.4, 0.3, 0.2, and 0.1. So just for completeness, what did we do? We started off with the situation where we wanted to calculate the probability of a column, G, G, and A. We had our branch lengths, and I assumed that we had A and an A here. I showed you that the Felsenstein pruning algorithm allows you to calculate the probability while not conditioning on any particular combination of nucleotides that marginalizes over the ancestral configuration of nucleotides. And I also told you intuitively where these transition probabilities and the stationary probabilities come from assuming a continuous time Markov process is describing how characters, DNA sequences, whatever they happen to be, how they're evolving. Now, where did the rate matrix come from that I was showing you guys? All right, so that was all as an example. It's not like I estimated it from some data. I just picked it out of the blue. And where, what did I do? Well, this is the rate matrix I used. This is the parameter, kind of a generic rate matrix. This is called the HKY85 model for Hasegawa-Kishino-Yano model. You might have heard of this. This is what the rate matrix looks like. Notice it has some parameters. It has this parameter kappa, and it has the pi's, pi A, C, G, and so forth. I'll get to this in a second, but these are the values I chose. I chose kappa equal 5, and I chose pi A, C, G, and T to be 0.4, 0.3, 0.2, and 0.1. I just thought it was kind of cute to have a 5, 4, 3, 2, and a 1. I don't know. I had to choose something. And this, if you go ahead and plug these numbers up here, this is the rate matrix you get out. Two things I want to point out here. The first I'll show you is that if this is the rate matrix that pops out, if you plug these numbers in here, then if you look at this number here, pi g, right? That's this entry. So say, well, what's pi g? It's 0.2. And so where's the same entry down here? It's right here. Right? That's not a 0.2. Right? So what's going? So I must have told you a lie at some point or simplified something. Well, notice there's this little mu here. That's a scaling factor. All right? So what we do is we scale these rate matrices such that the average rate of change is 1. Okay? And so what I did is initially I had a 0.2 here, but then I rescaled all the numbers in that rate matrix so that the average rate's 1. I don't think I'm going to be talking about how to rescale the rate matrices so the average is 1. It's not difficult, but if you're interested, I can show you. It's not conceptually difficult. It's a weighted average. So that's the first thing I wanted to say. And the second thing is I describe the stationary probabilities as you have a rate matrix that's fixed, and you run the process for a very long time, formally speaking, infinitely long. What's the probability of capturing the process is A, C, G, or T. Notice that in this phylogenetic model, these stationary probabilities are built into the rate matrix in a peculiar way. Pi t is found as a factor in this column, g is a factor in this column, and so forth, right? Phylogenetic models are a little weird. I mean, what I told you is absolutely true. Stationary probabilities really are the long-term behavior of the rate matrix. The probability of capturing the process is an A, C, G, or T. But in phylogenetics, we parameterize the rate matrix so that it will have a particular stationary distribution, right? And you do that by putting them in here. So we basically have a way of controlling what the stationary probabilities are as parameters of the model, right? So just keep that in mind. And there's a reason why we did that, or not we, but Hasegawa, Kishino, and Yano and others did that. It's because people observed that if you had, well, I'll tell you later. Anyway, so that's where the rate matrix I was showing you came from. Right? Just 5, 4, 3, 2, 1 is cute, and so that's what I did. All right, so here's some other rate matrices that are often used. If you've heard of the Jukes-Kantor model, this is the rate matrix, the scaled rate matrix. Notice there's no scaling factor here. All the off-diagonal parts are 1/3. And the diagonal parts are -1. Here's the Kimura 1980 model, the scaled version of it. Here's the HKY85 model, the unscaled. Notice there's this little factor mu. And then there's this model called the General Time Reversible Model, GTR, and this is the rate matrix. It has the stationary probabilities, these pi's, but it also then has these, what they call exchangeability parameters, RAC. So you see RAC appears twice, RAG appears twice, RAT appears twice, and so forth. But there's 6 exchangeability parameters in that rate matrix. Importantly, under any of these models, once you specify them, you can calculate transition probabilities easily just by matrix exponentiation. Right? Sometimes there's formulas that you can use too. If you look at these models too, you'll notice there's a time element. The first model of DNA substitution, first continuous time Markov model, that was described was by Jukes and Kantor in 69. Then you have this modification by Kimura in 80, the Hasegawa, Kishino, and Yano in 85, and then Tavare shortly after that in 86. These are more complicated models as you go in time. But really, if you think about it, this is the simplest model. It's making the statement that rates of change among all pairs of nucleotides are the same. Okay? And then in the late 70s, people are starting, or mid to late 70s, people are first starting to sequence DNA sequences from species. And one of the first things they observed were that transitions are occurring at different rates than transversions. So transitions, it's kind of confusing because we're using transition in more than one way now. But if you think about A, C, G, and T, well, changes between the two purines or the pyrimidines, these are, those are transitions, right? And then the other changes are called transversions in the molecular evolution literature. So they were observing that these types of changes between A and G or C and T were occurring at a much higher rate than the others were occurring. And so people said, well, shoot, you know, if you look at the Kimura model, or the Jukes-Kanner model, it says that all those things should be occurring at the same rate. This model sucks. I'm not going to do any of this stuff because this is a bad model, obviously, and I don't like using bad models, so go away. And Kimura said, well, wait a second. We can modify this model so that we have a parameter kappa, which is the transition transversion rate ratio, right, which will accommodate observations that transitions are occurring at a different rate than transversions, right? And then, of course, they started saying, fine, that's great. People were collecting more data and saying, well, wait a second. Both these models, the Jukes-Kanner and Kimura model, have stationary probabilities which are 1/4. 1/4 for A, C, G, and T. They're all equal. And say, but if I look at and that would predict that if you looked at your DNA sequence, your alignment, that would predict roughly equal composition of A, C, Gs, and Ts. And they're saying, geez, my sequence has way more G than anything else. What am I going to do? This model stinks. Both of these models stink. So HKY, these guys, Hasegawa, Kishino, and Yana, said, well, fine. We'll modify the model so we still have a transition transversion rate ratio to accommodate the fact that transitions are occurring at a different rate or a higher rate than transversion, typically higher rate than transversions. But we'll also do this little trick where we'll add these parameters, which people will, you know, if you ask biologists, they'll always call these the base frequencies, right? Because that was the initial idea, that we'll modify the stationary probability distribution so that you would predict different frequencies of A, C, G, and T in the alignment. That's what they did. And they did it using the trick, which was to control the stationary probability distribution of the matrix, right? And then Tavare said, okay, end of game. This is the most general model that's time reversible that you can have, and everything else is just a special case of this model. So there, right? So he took his ball and everybody had to go home after that because there's no more models to describe. They're all special cases of this. What else do I want to say? All right, so time reversibility is a specific behavior of these continuous time Markov models where, in a sense, they look kind of the same, run forward or backward in time. You wouldn't be able to distinguish. If I showed you the sequence of changes, you wouldn't be able to tell which way it was run, unless I told you after the fact. From the perspective of phylogenetics, the only thing that matters is this, is that when you have a time reversible model, you can't determine the root of the tree. That is to say, different rootings have the same likelihood for the same tree, right? If you maintain the branch length sums in a particular way. But there's no way of identifying the root of the tree with a time reversible continuous time Markov model. And that's why these programs return unrooted trees. And you have to root it with a secondary criterion like the outgroup criterion or assume a molecular clock or something. That'll give you rooted trees too. But there's no need, or there's no rule that's been written down by somebody like Felsenstein saying that you can only use time reversible models. You can use non-reversible models. And this would be an example of a non-reversible generic 11 parameter model. If you were to calculate the likelihoods on this tree, you'd have to do two things. First, you'd have to deal with rooted trees in computer memory. And secondly, you'd have to figure out what the stationary probability is for that rate matrix. You have to solve a particular equation, which is solvable and easily solvable, but you'd have to do that so you know what to, how to deal with the root probabilities. But you can do that, and I know Zhiheng Yang had a paper in the mid-90s where he used non-reversible models, and I had a paper in the early 2000s where we used non-reversible models. But there's nothing illegal about using non-reversible models. And is that something we have in RevBayes yet? And we have it in RevBayes, which is pretty cool. Okay. Before we do the next step, which is I'm running a little bit longer than I thought. I'll have to consult with my colleagues about what to do. But here's an example of a continuous time Markov model that might be appropriate for amino acid data. Okay. So the point I want to make here is that I was talking about DNA sequences, but you can people modify these rate matrices or the continuous time Markov model to account for other types of data that we come across. If you had an alignment of amino acid sequences, instead of having 4 states, A, C, G, and T, it might be sensible to have the states be the different amino acids, all 20 of them, right? So your rate matrix would be 20 by 20, where we have along the columns and rows of the table the possible amino acid states, and then you'd have to come up with a way of specifying all the different rates, right? So it's hard to see this, but here I actually specified it as kind of like a model. It's like an amino acid GTR model, General Time Reversible Model, where you'll see there's 20 amino acid frequencies, pi A, pi R, pi N, pi D, pi C, specified just like they are in the GTR model that I showed you earlier. And then you have these little exchangeability parameters. And instead of having 6 exchangeability parameters, this matrix has 190 of them. All right, but same thing, right? It's like, that seems like a lot of numbers to me, but to the computer, they're just numbers. And as long as you have the inference machinery behind it, you can often estimate these parameters. It's matrix exponentiation, everything works the same. It just takes a little bit longer because the matrices are bigger. Felsenstein-Pruning algorithm works just the same, but instead of summing over 4 things, you're summing over 20. So what it means is a programmer, you go into your code and you search and replace for 4. You say, okay, there's a 4, change that to 20. That's not what really happens, but it's equivalent to that conceptually. You might have a parameter like n states that would be 4 or 20 or something. So what I want to do next is take a minute and have an open conversation with Sebastian and the others back there. You know where I want to go, right? I want to do the simulations, but it takes time and I've only got 20 minutes. What do you think?
How long do you need for that?
It usually takes a full hour to do everything I want from here.
Okay.
We could start, I could do one simulation, then we could continue after break, but then that would be breaking into your time. What do you want? Okay, so we're flexible enough for that?
Yeah.
Okay, so I'm sorry, but the beginning part, which I was covered in more detail than I normally do, took longer. Okay, if you're okay with that, then that's what I'll do. So what I'm going to show you is how you actually do a simulation, and you guys are actually going to do that, okay? And what I'm going to do is I'm going to simulate DNA sequences for the rate matrix that I showed you guys earlier. Now you know where it came from, 5, 4, 3, 2, 1, right? But this is just a specific example of a HK-Y85 model. And I want to simulate data on this tree. I just chose this tree out of a hat, or just chose it, not actually out of a hat, I just made it up. And here are the branch lengths, 0.3, 0.1, and so forth. And I label the species 1, 2, 3, and 4. Now, what I'm going to do is I'm going to show you guys how to do this once, and then I'm going to give you random number generators, and you're going to do this yourself as well, okay? So I'm going to give you one example, and then you're going to do it yourself. And I guess I'll do it on the board over here. So what I want you to do first is get a fresh piece of paper. You don't have to do it now, but when you do the simulation, get a fresh piece of paper, and you just kind of trace out the tree. And maybe write down somewhere the branch lengths. All right? That's the first step. And when we do this simulation, we're going to do it from the root to the tips, first of all. Although in principle, we could do it any point in the tree, it just would be more complicated. But we're going to go from the root to the tips. And we're going to do it branch by branch. Okay? So we're going to do it branch by branch, root to tips. So the first thing we need to do is determine what the nucleotide is at the root of the tree. We know it could be an A, C, or G, or T, but we want to start the process off down here. So what's the probability of it being an A here? Anybody? So somebody, I think I heard the number 0.4 came out, right? The probability that this is an A is 0.4. Why is it 0.4? It's because you know that I told you this is the rate matrix, and you guys all know that for this rate matrix, the stationary probability is 0.4, 0.3, 0.2, and 0.1, right? So what we're imagining is that there was a very long tail leading to this point right here, right? One way to think about this is that maybe we always start the simulation in an A way back here, and then we have a branch length of 1,000, right? So we say, okay, we're always going to start the simulation in an A, and we have a branch length of 1,000. So we do all the simulations, lots and lots of changes, maybe 1,000 of them on average, until we get to this point right here. Then whatever the simulation results in here is what we use. We know that there's a way of doing that a lot faster. Instead of like simulating way back here in time and spending the rest of the week doing this, you say, well, I know that with that rate matrix, the probability of the process being in 0.4, A is 0.4, based on some math. Right? So we'll take advantage of that. So we need to determine whether it's an A, C, G, or T, and this is how we're going to do it. First of all, we have to have a way of generating random numbers. Actually, we need to be able to generate random numbers on the interval 0, 1. And I've done that. Actually, brought with me random number generators. Here they are. They're dice. And these are the I went to games at Berkeley and got what I thought were very pretty dice. Each one of you can keep one of these. Take one and keep it. So you always have a random number generator on your hand. But this is a 10-sided die. And if you look at the faces of the 10 sides, they have 0, 1, 2, 3, up to 9. Right? So we can generate a random number between 0 and 1 by doing the following. We'll call it U. But we're going to take the 0 and the decimal place is given. And then we'll use the die to generate the 10th, the 100th, the 1000th, and so forth places. So if I, for instance, want to generate a random number, I could do the following. I roll it once, and I get the number 9. I roll it again. I got 9 again. And I roll it again, and I got a 2. And I could do this to get a random number between 0 and 1 to any degree of precision I want, right? But right now I generated a random number that's random on the interval 0, 1, that's 0.992. And if I were to do this process again, I could generate another random number, okay? So we have a random number generator. Good. Probably actually better random number generator than you can get on a computer. And in this particular case, we want to generate one of 4 events. So what I'm going to suggest is that if the number we generate is between 0 and 0.4, we say that we have an A at the root of the tree. If it's between 0.4 and 0.7, we'll say we have a C. If it's between 0.7 and 0.9, we'll say we have a G. If it's between 0.9 and 1, we'll say we have a T. Can everybody see why, if I set my intervals up in this way, that it will end up generating an A with probability 0.4, a C with probability 0.3? Raise your hand if you don't see it. It's nothing to be ashamed about. So the idea is that if this interval here, because this uniform, this random number we're generating, it's a flat, right? So all different possible values between 0 and 1 have an equal probability. So what we're saying is that this is 0.4 right here, and this is 0.7, and this is 0.9. This area here has an area of 0.4. This area here has an area of 0.3. This one here is 0.2, and this last little interval is 0.1, right? Basically, that's the probability that when I roll the die that I'll get a number between 0 and 0.4 is 0.4 because it's flat, right? Now, that said, I mean, this is what I would suggest doing, right? But as long as the intervals, 2 things, as long as you make up your intervals before you roll the number, and as long as they have the appropriate probability, you can choose any interval you want. So as an example, I could also say that, well, if my random number is between 0 and 0.2 or between 0.8 and 1, then I'll say it's an A, right? That would be an alternative interval I could use. You can see that between 0 and 0.2, that's 0.2. Between 0.8 and 1 is 0.2, so the sum of those 2 intervals is 0.4. That gives us the appropriate probability, but it's a pain in the ass to use, right? So why would you do it? But you're welcome to do any stupid interval you want, just as long as you choose it before you roll the die. We're going to do the simple thing, because you're less likely to make a mistake. So I've chosen my intervals. Now I'm going to roll my die. I'm just going to do the 2 decimal places to determine what's at the root of the tree. This is the real roll now. Ready? 0, 6. So what happened was, well, the most probable thing, we have an A at the root of the tree. So I put an A here, okay? With me? We've hardly done anything. All we know is that there's an A at the root of the tree. But now I'm just going to use this rule that I'm always going to simulate to the left before I go to the right. So let's go ahead and determine what happens along the left branch here. Well, now we have to generate a new kind of random number. We have to generate our exponential random number. Remember I told you the waiting time till the next event is exponentially distributed? Well, we know what the rate is. If we can read the rate from the table. We know we're in A, so the rate of change when we're A is 0.886, right? So we know the rate of the exponential. We just don't know how to generate an exponential, right? And this will generate, the die generates a uniform 0, 1 random number, but there's no die in the world that generates exponential random numbers that I'm aware of. But this is the cool thing. We can transform a uniform into an exponential. So if we use the following equation, t equals minus 1 over lambda natural log of u, you can take a uniform random number and transform it into an exponential random number. Okay? So that's what we're going to do. I'm going to put 3 numbers here. One will be our uniform. I'll keep this up here so you remember it, have it. We'll have our uniform, we'll have our lambda, 0.886, and we'll figure out what t is. And what you need is you need to have a calculator with a log function, natural log function on it. If you have a phone, a smartphone, of course you have that. So on the iPhone, you have a calculator that comes with it. You turn it on its side, it becomes a scientific calculator where you'll find the natural log. So first thing first, generate your uniform. So I'm going to generate my uniform number, 0.62. 0.62. Now I do math, right? I know what lambda is, I know what u is, so u and lambda. So now I just do my math. So I say 0.62 natural log divided by 0.886 equals, so it's 0.54. See if you get the same number, right? So that means the next event is going to occur at 0.54. Well, our branch is only 0.3 in length, right? So that means that the change would occur about here. You see that? But the important point is this. The simulation was running, it was an A. When it got to that point in the tree, it was an A. Right? It doesn't matter that where in the future after 0.3 it occurs, just as long as when you've passed the end of the branch, what state was it in? All right, so now we've finished the simulation along this branch. We're done with that branch. But now we needed to go along this branch. So we go back here and we erase. We still have the same rate. It started in A still, but we need a new random number generator, new random uniform number, and a new exponential. So I'm going to go ahead and roll my die, 0.28. Do my math. So take 0.28 natural log divided by 0.886 equals 1.43. So 1.43 is when the next event occurs. We're only doing it branch by branch, so you can forget everything else on this tree, the fact that there's stuff up here. The point is this, that 1.43 is greater than 0.1, so we're an A here as well. With me? Okay, so now we've done this part of the tree. Now we need to do this part. So I'm going to go left, then right. Just use, you can go right, left, or whatever. Just as long as you have the ancestral state before you begin things, you're good to go. So once again, we need a new random number, new time, exponential time. So I'm going to go ahead and roll 0.91. So let's go ahead and figure out what that is. So 0.91 natural log divided by 0.886 equals 0.94. Okay, so that's interesting. So 0.094 is less than 0.1, but just barely, right? It's right about there, right? So that means that we're A all the way to that point in the tree, but at that point we changed from A to C, A to G, or A to T, right? So we have to decide which of those 4 things it is. So I'm going to figure out, so let's think of the 4 or 3 possibilities. It's going to be A to C, A to G, or A to T. Those are the 3 possible changes we can have, true? What's the probability it's an A to C change? Well, it's an A to C change with probability 0.19, put semicolons there, 0.19 divided by 0.886, right? It's an A to G change with probability 0.633 divided by 0.886, and it's a change to a T with probability 0.063 divided by 0.886, right? Just read that from the rate matrix. Now we have to do the division. This is more tedious, but so we have 0.19 divided by 0.886 equals, this is 0.21. So 0.633 is 0.71, which means that this is going to be 0.08, all right? With me? Yes.
The equation to convert the uniformly distributed number should be 1 minus u.
It doesn't have to be. It could, so you just go from infinity, go from, I'll show you in a second. But it doesn't, it's symmetric, but I can show you how you can get this out of the other one. But yeah, you guys were working the calculus back there, I'm sure. But yeah, this works. So anyway, so let's think of our rules. So we want to get A to C change with probability 0.21. So if we have a change, if the random number, uniform random number is between 0 and 0.21, we'll say it's this thing. If it's between 0.21 and 0.92, we'll say it's a change from A to G. If it's between 0.92 and 1, we'll say it's a change to T. Okay, you see that? So we had to do more math, but we're just reading numbers from that. Now we're going to generate a random number. We have to do another random number to determine which change it is. So here goes, 0.31. 0.31 is this one, right? So we have an A to G change. So now we know we have an A to G change right there, but we still have to finish the simulation, right? We have just a little bit more. So this is 0.94, 0.094. So we have 0.06 to go, don't we? So we have to formally, I mean, it thinks like, well, shoot, probably nothing will happen. So we'll just say it's a G. You can't do that. It almost certainly will be a G, but you have to do it. So we have to generate one more little exponential to finish, or at least one more exponential to finish this off. So I'm going to erase this math. What's our rate of change when we're a G? Anybody? 1.519. So our rate's higher. Now we'll generate our exponential, 0.66. So 0.66 natural log divided by 1.519 now. That is equal to 0.27. We only had 0.06 to go, right? But we now know that we really are a G right there. Okay? All right, so let's do the last. Let's do this branch next. Oh, what's it? So here for this branch, we're not G. The ancestor of this branch is A, right? So we have to go back to 0.886. So generate a random number, 0.88. So natural log, or 0.88, natural log divided by 0.886 equals 0.14. Oh, we have another change. Okay, so this one, so that's 0.14 is about there, right? So we have an A up to this point. This is a 0.14, just so I don't forget. We have to figure out, is it a change from A to C, A to G, A to T again? And of course, I erased these numbers, but I do remember them, I think. It was 0.08 here, 0.71 here, and 0.21 here, right? So once again, 0 to 0.21 is A to C, 0.21 to 0.92 is A to G, 0.92 to 1 is A to T, right? So this is going to be A to C, A to G, A to T. Okay? Let's go ahead and determine which of those it is. 0.80, 0.80, so we have another change from A to G. We have 0.06 to go. So let's go ahead and continue that. You can see how the computers are really useful sometimes. They could do it so much more quickly than this. But this is like, I hope you get the idea. So now we have a different rate. So what's our rate again? 1.519. What's a random number? I don't know. We have to do that. 0.83. So 0.83 natural log divided by 1.519 equals, oh God, that was close, 0.074. So we almost had another change, but we didn't, thank goodness. We had a 0.06 to go, but our random waiting time was 0.07. So importantly, by the time we got here, we were a G, right? I'll make that prettier. We were a G. True? Okay. So we have 2 more branches to go, and then we'll be done. We're at state G at the root of it, so our rate is 1.519. We don't know what these 2 things are, but we will find out. Our random number is 0.32. That means 0.32 natural log divided by 1.519 equals 0.74. Importantly, because I was going left first and right first, 0.74 is a lot greater than 0.1. So we're G here. And finally, or maybe finally, we don't know, perhaps finally, we'll do the simulation along that last branch. 0.82, I think that's going to be a change, we'll see. 0.82 natural log divided by 1.519 equals 0.13. Whew! No more changes, right? 0.13 is greater than 0.1, so we have a G here too. So if we were to think of this as an alignment, we have the species 1, 2, 3, and 4. We have species 2, species 1 has an A, and the others have G, right? Right? I want you guys, everybody in the class to do at least one simulation where you're going to be simulating your own column in the alignment. And then when you're finished, come up to the board and write your result here. How many changes did I actually have on this tree? I had 1, 2 changes, right? Also, when you write the result, down here near the bottom, make a little note about how many changes really occurred. It could be 0, 1, 2, 3, 4, and so forth, but like how many changes really occurred when you're doing the simulation. Write that down at the base of the tree, or down here off the alignment. But go ahead. Oh, wait, before we do that, you need random number generators. So here you go. If you want to exchange your die for a better color or something like that, I don't care. 2, 3, 4. So that's something that is predicted from these simulations. And in fact, one way we could test whether there's like a systematic problem with people's simulations is we could see if that was really significantly off from 0.9, but I'm sure everybody was doing it correctly. So that's the first thing to note. And the second thing is, in this class, we know how to calculate the probability of this alignment. We simulated an alignment, right? We know how to calculate the probability. We'd calculate the probability column by column, and then we would make the statement, let's assume that the substitutions were independent in different columns and multiply the probabilities together. Well, that statement, let's assume that the substitutions are independent, is actually true, right? Unless you were like cheating off your neighbor, right? And I'm sure nobody would do that, right? If you were simulating and you looked over and said, gosh, this person started the root with an A. I love A. That's my favorite nucleotide. I really want it to be an A. So you fudged it so that you got an A at the root 2, then you would have non-independence, right? And other problems. But I would wonder why you really like the nucleotide A so much. But anyway, that's so we really did adhere to the assumptions of the simulation. The other thing I want to point out is that we all saw me simulate this column, right? Do I still have it over here? I erased it, of course. But where do we have that? We had a single change. You saw, or no, 2 changes rather, and we know exactly what happened in my simulation, right? And so if our data actually came kind of like we simulated it here, where you had the tree and you could see where all the changes are, we would not have to do the matrix exponentiation or the Felsenstein pruning algorithm business at all. We would be able to calculate probabilities, likelihoods in a much different way. For instance, I'll just show you a very simple case. This one has to go. Show you a very simple case. Let's say we had A, C, A, and we know we had a change right here from A to C, and that this branch was 0.2, 0.1, 0.1, 0.1, okay? And we're going to use the same rate matrix, right? So how would we calculate the probability of this? Where we saw that this change, and we'll say this change was exactly at 0.07. So 0.07 here, 0.03 there. How do we calculate that probability? Well, we know every time we rolled the die, we would have a new factor in our likelihood. So for instance, we rolled the die, and we know we must have had an A at the root of the tree. What was the probability of an A? 0.4, right, under this model, right? Then we knew that we did not have a change along a branch of length 0.1. So you say, well, what's the probability of not having a change along a branch length of 0.1 when we're in A? It's e to the minus 0.886, which is the rate when we're in A, times 0.1. That's the 0.1. That's the probability of not having a change along that interval. And then we say, and we also had no change along this interval, so it'd be times e to the minus 0.886 times 0.2. That's the probability of not having a change in that interval, times the probability of not having a change here, e to the minus 0.886 times 0.1. I did get the right rate. Yeah, okay, good. Times the probability of not having a change up to the instant before 0.07, so it'd be e to the minus 0.886, 0.07, times the probability of having a change in that instant of time, which was 0.886, dt, I guess, times the probability of a change from A to C when it occurs, which is 0.19 divided by 0.886, times the probability of not having a change over the last 0.03 interval when we're a C, which would be E times E to the minus 0.696 times 0.03. Essentially, every time you roll the die to get, made a random choice, would add a new factor to this equation. Of course, this would be great because, first of all, it would be fast. There's none of this pruning algorithm business or matrix exponentiation. It's just all stuff that you could calculate lickety-split. And also, I'm sure that if our data actually came with the changes marked on the tree, we could probably infer some really awesome things about molecular evolution, right? Unfortunately, we don't get to see it, right? So we have to marginalize over our uncertainty, all the different character histories that could have given rise to the data. So we go back and we do the matrix exponentiation. But at least, for the person who generated the data, they could calculate their probability this way. If anybody else in the room who didn't see how exactly what happened, they would have to do it the way I described in lecture. Is that distinction clear? Because we could condition on more information here than we could when you don't know exactly what happened. The second, so we have to do it the old-fashioned or the Felsenstein pruning algorithm way, not the old-fashioned way. But if we want to calculate the probability of these columns, we have to do exactly what I described in lecture. And so here, I've given, there's, for the tree we had with 4 species at the tips, there's only 256 possible patterns that could have been generated at the tips, 4 times 4 times 4 times 4. And I made a table of all those probabilities. So sum up all the probabilities in this table and then the next page, and they sum to 1. So for instance, this pattern AGGGG, it has a probability of appearing of, here, 0.032738. So if I had, 1,000 students doing this, right, about 3.27% of them should come up with the pattern that I had, right? Of course, they're going to generate the pattern in numerous different ways, but that's the fraction of the time the student should actually generate that pattern. If we want to calculate the probability of this alignment we did, then we would have 0.03 whatever, 32738. That's the probability of that column. Then we have GAAA, so it's going to be times the probability of this pattern, GAA, I think that's the next page. GAAA. Oh, at the very top one, 0.045565. Right? That's the probability of the second column, times the probability of ATTT. That's going to be on the previous one, ATTT, right here. All right? That's times 0.004711, right? You get the idea here, right? We look up each pattern we simulated and multiply by, that's a new factor in this probability. We're multiplying numbers between 0 and 1. Whenever you do that, the product gets smaller and smaller and smaller. So if you were to do this on your calculator, what do you think would happen eventually? Sorry? It goes, well, it's not really 0, but the calculator says this number is too small to hold in memory, and if it's a good calculator, it should like give you an error, right? It'll say, give you an error. That's called it's a underflow error. So, in computer memory, we can't hold numbers with infinite precision, unfortunately, right? We only have a certain amount of memory to represent numbers. In fact, numbers like these real numbers are represented in computer memory with 8 bytes. So that's 64 bits, zeros and ones. So whatever is going on, whatever the machinery is, and it's not important you understand the machinery, it can't represent infinity with 64 things. It's just not possible, right? So it's always, whenever you're representing real numbers in computer memory, it's always an approximation to that real number. And so when the number gets too small, and these likelihoods will get smaller and smaller and smaller as the probabilities will get smaller and smaller and smaller as we add these or multiply these probabilities together, eventually you get an underflow error. Okay? So what do we do instead? Well, if you look at the probabilities that are reported by these computer programs, they're not probabilities, they're logs of probabilities. That's the secret. So what we do is, taking the log turns products into sums. So what we do is we take the log of 0.032738 plus the log of this number plus the log of this number and so forth. So we take the sum of the logs of these probabilities for the columns. You get a log likelihood out at the end of the day. Or log probability out at the end of the day. That's why the probabilities you're getting on these computers are negative numbers. They're negative log probabilities. Is that clear? And it's to avoid this underflow error. If we could store probabilities numerically in computer memory with no problem, of course we just do the easy thing. We have to take the logs of them to represent them accurately, or at least the log of the probability accurately. So I think that's what I wanted to say there. Is there anything else I should mention about the simulation that I should get out? We talked about why we use logs, how if we actually could see where the changes were, we would use a different way of calculating the likelihood, and we wouldn't have to use the matrix exponentiation or the Felsenstein pruning algorithm. We talked a little bit about what the branch lengths that we should expect, about 0.9 changes per, on average among all the students in the class. I think that's good enough. So I want to spend a little bit of time before we go to the next topic about how you can modify these models to these continuous time models, continuous time Markov models, to look at different situations. And I'll just start off with this example of a single-stranded RNA virus that I used to work with in my laboratory when I had a laboratory. It's a RNA. It's a bacteriophage, E. coli phage, and this group of RNA viruses probably has the highest measured mutation rate. It's about 10 to the minus 3 per site per replication, so it screams along. And the interesting thing is the RNA folds on itself. The genome is only about 4,000 nucleotides in length. That's 4 genes. The genome folds up on itself in the stem loop structure. Okay, and it's actually the unfolding of the stem loop structure that controls the translation of the 4 genes, right? And so you might imagine that natural selection acts to maintain these Watson-Crick pairs, right? So if you have a mutation in one of the Watson-Crick pairs, you might have a compensatory. Natural selection will favor a compensatory substitution that restores the pairing. And the problem with this is, that's kind of interesting biologically, I suppose, but in terms of calculating the probability of an alignment of different RNA phage, like from this group, it does mean that maybe this independence assumption is, we always knew it was bad, but this one's kind of in-your-face badness, right? It's like, this is really, are you sure? And for a long time, people used ribosomal genes, still use ribosomal genes as phylogenetic markers. Kind of the same issue comes up there where the ribosome, under very strong natural selection, that's why we can compare it across all of life, right? It must have been. It is. And so these stem loop structures that are part of the alignment are very clearly they're not independent. The Watson-Crick pairs aren't, the nucleotides participating in a Watson-Crick pair aren't independently evolving. So people realized this in the early 90s. Schoeniger and von Hessler said, well, in these ribosomal cases, we can actually identify which nucleotides are paired up in these stems. So why don't we use that information and model each Watson-Crick pair together, right? So instead of modeling them independently as 2 4x4 substitution models, let's model them together, in which case we think about the state space of our continuous time Markov model being all the different pairs that could occur. Well, there's 16 of them, right? And here we have it. A, C, A, G, A, U, because we're dealing with RNA and so forth. So our state space is all 16 pairs. Remember, understand a continuous time Markov model. What are the states? What's the rate matrix? Well, the states are the pairs, and then the rate matrix is, well, you have to decide. The nice thing is that, well, whatever it is, we know what to do with the diagonal. That's not a problem, right? Because we know the diagonal is specified by the off-diagonal parts. So whatever the diagonal elements are, we don't worry. But we do have to worry about the off-diagonal parts. Now, the other cool thing about this is a lot of the entries in the rate matrix are 0. And why is that? It's because this is a one substitution at a time model. All these models are. They only allow one event to occur in an instant of time. And so that means that going from GU to AA involves changes in both of the nucleotides, right? That's 2 changes in an instant. So those have a rate of 0. Now that doesn't mean that you can't, over evolutionary time, have a transition between, say, a GU and an AA. It just has to go through more than one intermediate change, right? It has to go through at least 2 changes to get to there. That still leaves these blanks, like, for instance, going from UA to AA. That involves a change at the first position here, one of the first nucleotide in the pairing. That can occur in an instant of time. And then the question is, well, how do you specify those parts? Well, you put some number there, right? And so how do you specify it? Well, here's one way you can do it. This is a different way, a different notation for specifying the rate matrix. This is like specifying the rules that allow you to fill in each cell in the rate matrix. So what this says is Qij, this is the ij that's like one of the cells in the rate matrix. That is going to be 0 if I and j differ at 2 positions, like I showed you. It's going to be pi j if it's a transversion change, that one single change is a transversion, and it's going to be kappa pi j if the single change is a transition. This is kind of like an HKY85 model, but for doublets. Right? This is called the doublet model. So what do you do? And it was from Schoeniger and von Hessler in 1994. So that's the model. The machinery you use to calculate the likelihoods is precisely as what I described. You change all the 4s to 16s, and you're good to go, right? That's all you do. So you're exponentiating a 16 by 16 rate matrix. The Felsenstein pruning algorithm has sums over 16 states and so forth. But otherwise, it's the same thing. Here's another model you might have heard of. These are so-called codon models. So if you have a protein coding DNA sequence, you can actually account for the non-independence within a single codon. So a codon being the triplet of nucleotides that codes for a single amino acid. Right? So if you're modeling the process on a codon, it's essentially what you're doing is you're expanding your model around a triplet of nucleotides. So your state space is now the 64 possible states, triplets. So there's 4 times 4 times 4 possible states. So your rate matrix is going to be quite a bit bigger, and in fact, I'm just showing you part of it, the little corners of it, but there's a lot of states that are unshown, but 64 by 64. Here's the different possible states. You can go from codon AAA to AAC and so forth. Again, this is a one substitution at a time model, so you can't go directly from TTA to AAA, in an instant of time because it requires changes in the first and second codon positions. You see that? But there are a lot of changes that are allowed in an instant of time. Going from, for instance, from AAT to AAG only involves a change at the 3rd position. So how do you specify these models? Well, there's a bunch of different ways you can do it. But here's one that was used, a model that was used by Nielsen and Yang in '98. Once again, you put a 0 in the cell if the 2 codons differ, the starting and ending codon differ at 2 or 3 positions. You put a pi j in if it's a synonymous transversion. The single changes the transversion and synonymous. So a synonymous change, just in case you don't know. So the genetic code is redundant. 20 amino acids, 64 possible codons. So there's a lot of changes that in the sequence which will not change the amino acid that's coded for because of this redundancy. So those are called synonymous changes when they don't. Non-synonymous changes are ones that a change in the DNA sequence which also changes the amino acid that's coded for. Clear? So if the single change is synonymous and a transversion, then it's pi j. If it's a synonymous transition, kappa pi j, just like the transition-transversion rate ratio we had earlier. If it's a non-synonymous transversion, you have this new parameter omega, which is the non-synonymous synonymous rate. Okay? And if it's a non-synonymous transition, it's omega kappa pi j. So that's how they model it. So you have this new parameter which you can estimate, which is the non-synonymous synonymous rate ratio. Typically that rate ratio is estimated to be much less than 1 for most DNA sequences because, you change the functioning protein, typically you break it. And so you have natural selection, purifying natural selection, removing those mutations from the population. There's this idea of modeling non-independence. You can with the doublet model, we're saying, okay, we can identify these two nucleotides as being involved, non-independently, so we just expand the model around those. The codon model is the same idea. We just expand the model around the triplet, right? But you might say, well, can't we just do this for the entire sequence, like have an arbitrary model of non-independence? And the answer is yes, right? You just expand the model around the entire sequence. Now you might say, well, then what's the state space? Well, if your sequence is 100 nucleotides in length, and each nucleotide position, each position in that sequence can have 4 states, well, you have 4 to the 100th possible sequences, right? So so the state space of your continuous time Markov model has 4 to the 100th possible states, and the rate matrix is 4 to the 100th by 4 to the 100th, right? It's a very big rate matrix, right? And so we can always make these statements. We can. Some people are smiling and say, that's stupid, right? And in some ways it is, but it isn't, because these guys actually said, let's do it. This is from Robinson et al. They said, this is an example where our sequence, our alignments are only 6 in length, so our state space is only 4,096 possible nucleotides, right, instead of 4 to the 100th, but it's the same principle. If your nucleotide sequences, if your sequences were 1,000 in length, the state space would be 4 to the 1,000th, right? Once again, we can talk about the model, it's just like, well, how do you do the calculations under it? So just bear with me. So here we have the sequence model. Once again, we don't allow more than one thing to occur in an instant of time. So even though we have this huge state space and this huge rate matrix, most of the entries in this rate matrix are 0. In fact, if you imagine going from this sequence, T, 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 to any of the others, well, how many of them have positive numbers? Well, you can only go from this sequence to others when they differ at one position here, right? Right? Because if they differ in 2 positions, the rate's 0. So for instance, we can go from T, 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 T to T, 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 A. That's allowed, right? You got it? So how many such sequences are there? Well, each one of these positions you can change to 3 places, right? So we have 3 times the sequence length, or 6, 18 entries that are non-zero. Everybody else, all the other entries, 4,000 whatever, 3,000 whatever, are all 0, but only 18 are not. So that simplifies, and that's true. So if we had a sequence that was 100 in length, right? Once again, we have 4 to the 100th possible states, but only 300 of them are not 0. All right? So that seems to simplify things a little bit, and Robinson et al. Said, yes, it does indeed. Because what we can do is we can take our sequences, the observed sequences, and put them at the tips of the tree. There they are. And then what we're going to do is we're going to populate the tree with intermediate sequences, like I've shown here, each of which differs from its neighbors at one position. So for instance, look at this one and this one. This one has yellow here and this one has blue here, but the colors everywhere else should be the same, right? This one differs from the guy up here at only one place, red, yellow. So you should only see sequences differing at one position from those directly above or directly below. Got it? So what I'm saying is you populate the tree with a character history that when taken together would give you the data at the tips of the tree. Right? Now, the problem with that, of course, is you're saying you're just making up a character history that's consistent with the observations, but you can't trust that because you don't get to see them. You don't ever see them. But 2 things. One, if I were to give you a character history where not only do is the sequence of events consistent with the observations, but they were at specific times, then using the rules I showed you over here, I could calculate a likelihood, a probability. I'd be able to say, at least I'd be able to say, well, if this were true, here's the probability under this rate matrix. And then what we do is instead of using matrix exponentiation and the Felsenstein-Pruning algorithm to sum over all the different character histories, that's what they do, right? Instead of using those 2 algorithms, what we do is use Markov chain Monte Carlo to propose new character histories. Now, you don't know much about Markov chain Monte Carlo, but it's a way of sampling things in proportion to their probabilities, and you'll learn a lot more about it over the course of the next few days. But what we do is we substitute Markov chain Monte Carlo in for the matrix exponentiation and the Felsenstein-Pruning algorithm. Very clever paper, I think. The only downside is nobody's figured out how to do this on a tree that's not fixed. The topology has to be fixed. The branch lengths and everything else are allowed to vary. So you kind of have to be pretty certain about your tree to use this machinery. But it does mean you can investigate potentially quite interesting and arbitrarily specified models of non-independent change on a tree. The framework is there, at least, and that's it. And that's you guys now understand, I hope, at some basic level what's happening and why that's going, except for the Markov chain Monte Carlo, which I don't expect you to know yet. Okay, a little bit about rate variation across sites. Here's a tree, and those are the branch lengths, okay? Now, if we were to simulate, so there's different ways of accounting for rate variation across sites. The idea being that selection acts differently at different sites, maybe constraining what can happen at different sites differently. But most of the methods that are out there work as follows. We imagine that every site, every column in your alignment has its own independently chosen R, a factor R. If R is 1, and R is 1 for every site, then you're not changing the branch lengths at all. That's equivalent to equal rates across sites. But let's say R happens to be small. Let's say it's 0.1. What that means is that all the sites, all the branch lengths in your tree get shrunk down proportionally, right? But to be 10 times smaller than they were before in this specific example. And we know then that you'd have very little opportunity for change. The simulation machinery would be such that we wouldn't expect to see a lot of changes on a tree that all the branches were proportionally shrunk to be smaller. Similarly, if R happened to be a large number, greater than 1, then you're expanding your tree and you have more opportunity for change, right? So the question is, how is R chosen? Well, we could try to estimate it using maximum likelihood and whatnot, but turns out you don't have a lot of information in a single column in your alignment to estimate that very reliably. So what they do is they assume that R is drawn from some probability distribution. And one that you've heard of is probably gamma distributed rates. Many of you have at least. What that means is that you assume that this parameter R for every column is drawn from a gamma distribution that's specified. You guys all know that the gamma distribution has two parameters, the lambda, what I called lambda and k, right? Well, the more generalized gamma, same probability distribution, but instead of lambda and k, they call it alpha and beta, the shape and the scale parameters. What you do is you set the shape and scale parameters to be equal to one another, which means the gamma distribution has a mean of 1, and you draw the rate parameter for each site from a mean 1 gamma, right? What that means is that when we calculate the probability of the data at a site, we condition it on the parameter alpha that we chose to parameterize the gamma distribution with, and all the other model parameters, tree, branch lengths, whatever. But the important point is, because we don't know what value we're going to marginalize over different values of R, we're not going to assume that the data came from any particular value of R. We want to account for all the different possible values of R it could have come from. We marginalize. We have to integrate over all the possible values of R. And now, just to clarify this, if we were to simulate our DNA sequences with gamma distributed rate variation, this is what we would have done. I would have shown you the tree, I would have shown you the branch lengths, I would have shown you the rate matrix, right? The tree, like I did. But I'd also write down on the board, and let's assume that the gamma shape parameter is 0.3, right? That would be completely specifying the model now. What you would then do is, before you did your simulated site, the first thing you would do is you figure out what your personal R is, right? You would have to have a way of generating, I didn't show you how to do this, but you'd have to have a way of generating a gamma distributed random variable. There's ways of doing it on the computer. Dice, it would be a pain in the neck. But you'd do that. So you'd say, okay, I draw my R from a gamma distribution with parameter 0.3, 0.3, 0.3. You get your R, and you say, okay, my R happened to be 1.3. Let's say that's what you drew, you randomly drew. Then what you would do is you'd have to go through, before you did any of your simulation stuff like you did, you would multiply all the branches in the tree by 1.3, and that would be the tree you'd work on. You would have more simulations than your neighbor if that neighbor happened to draw an R of 0.05, right? Because he or she is going to be working on a tree that's much smaller, right? It makes sense? So, you might have an R of 1.3, next person might have an R of 0.23, 1.69, 2.41, whatever. Everybody would have a different R. What we could be assured of is that on average, the rate values that you guys all chose should be about 1, because we specified a mean 1 gamma. But everybody would have their own R. That would be a way of simulating a gamma rate variation across sites. But when we calculate probabilities of a data when we don't know what R is, we account for all the different possible values of R that it could have been by integrating it from 0 to infinity. Okay? It's a weighted average over all the possible values. Turns out that this integral is impossible to do analytically, except for a few simple cases. So what people do is they take the mean 1 gamma, and this is showing you different gamma distributions with different values of alpha, 0.5, 1, and 10. So the smooth curve is showing you what the distribution looks like for these different scenarios. But what you do is these computer programs break the gamma distribution up into equal categories. So let's say you're going to break the distribution into 4 categories. It breaks it into categories such that each one has an integral or area underneath it of 1 over the number of categories, 0.25 in this case. Then you use the mean or sometimes the median value for that category to represent all the rate values in that category. So here you'd say we're going to use this value, which we'll call R4 for the rate for the 4th category, to represent all the values from here to infinity. Use R3 to represent all the values all possible values of R between here, and so forth. But what that means is that you turn that integral into a sum, which you can do pretty easily. Right? So you have a sum over the different number of categories you broke the continuous gamma into, and you use the rate value, the average rate for the kth category. And because you broke the gamma into equal rate categories, each category has a prior probability of 1 over the number of categories you broke it into. And that's what we end up doing. And so if you were to use gamma distributed rate variation in a program like POP or Mr. Bayes or any of these, if you break it into 4 categories, you'll notice that the program runs about 4 times longer than it did when you had no rate variation. And that's because it's calculating the likelihood 4 times or 5 times, however many categories you broke it into. It has to calculate the likelihood independently each time. Anyway, so that's the gamma distributed rates. There's another model called the proportion of invariable sites model. If you were to simulate under this model, what you'd have to decide before is not alpha, but rather a parameter called p, which is the probability that the site is incapable of change. So you say, maybe we say p is, here 0.3. So you generate your random number between 0 and 1. We could actually have done this model, right? You generate a number between 0 and 1. If the random number was less than 0.3, you would say that R is 0, and you'd multiply all the branches in your tree by 0, and you would be done with your simulation the moment you determined what was at the root of the tree. Because if there was A here, there'd have to be an A at all the tips. If there was a C here. So basically, if you generated an R of 0, then 40% of the time with the rate matrix we used, you'd get an A, and you'd have all A's at the tips. 30% of the time you get a C at the root, and you have a C at all the tips and so forth, right? But the other times, if you didn't get R, then you would multiply all the branches by this number, 1 over, in our case, 1 minus 0.3, 0.7. So all the branches would be multiplied a little bit bigger, okay? And you'd go ahead, multiply all the branches, and then do your simulation as you normally would. So it's a proportion of an invariable site. So an invariable site's one that can't vary, right? And so it's it's just a 2-category type model. That's a proportion of invariable sites model. Very easy to simulate under. We could have done it. But the important point is that when we calculate the probability of the data at a site, because we don't know beforehand whether it's invariable or not, then we have to, when we calculate the likelihood, we have to do it twice. Once assuming it's invariable, that is to say rates of 0 times a prior probability that the rate's 0, and the other time with that it's a variable site where the rate's this thing, and this is the 1 minus p is the prior probability that it's a variable site. Is that clear? Weighted average again, marginalizing. And so what I'm going to show you is another cool variant on these models, and I'm almost done. So I want to set the situation up like this, where we have a tree, and it has 2 clades with lots and lots of species in them, right? So, and just to make things even simpler, we'll assume that the 2 clades diverged at about the same time, and they have about the same number of species, okay? So 2 clades, big clades, and diverging about the same time. And let's say in some column in our alignment that for all the species we see A here, okay? So we're just looking at a single column. Intuitively, do you think this is a high rate site or a low rate site? Sorry? Just shout it out. Worst thing, it's only 2 possibilities. You have a 50-50 chance. It looks like a low rate site, right? Because if it were a high rate site, we'd expect to see at that column more variability. You guys know that because you should have some intuition from your simulations. If you're multiplying all the branches by a number that's small, then your tree gets proportionally bigger and you have less opportunity for change when you do the simulation, right? So this would be the type of pattern we'd expect if this were a low rate site. And similarly, I'll answer this one for you. This looks like it could be a high rate site, right? Because we see more variability, A, C, Gs, and Ts at the tips, right? So this looks like a site where when we generated our gamma distributed random variable, for example, we must have multiplied all the branches up, so we had a lot more opportunity for change. Well, how about this pattern? Remember, so this is one column in our alignment, right? This one looks to me as if this clade is a high rate, the site would be a high rate clade, for this clade, but it looks like the same site, same position in the column in the alignment is low over here. This is a pattern that isn't really predicted by the proportion of invariable sites model or the gamma model, is it? Because those models say you expand or contract all of the branches proportionally up or make them proportionally bigger or proportionally smaller. This one looks like somehow you're warping the tree, making it bigger here and or making it smaller over here, right? That's what it kind of looks like to me. So this is a model that, of course, any of these models will give you a probability, but it doesn't look like this pattern is very well explained by either the gamma or the proportion of invariable sites model. So it turns out there's a model, or several models, but here's an example of one that can model this situation, right? So I'll explain how this is done. So what we imagine is that our nucleotides, A, C, G, or T, have a subscript on them, right? So and if you look at the chromatograms very carefully as they come out of the sequencing machines, there's usually a subscript there, 0 or 1, if you look very carefully. I'm joking about that, but we imagine there's a subscript there, okay? 0 or 1. So that means that there's two kinds of A's. There's an A with subscript 0 and an A with a subscript 1. The T with a subscript 0 and a T with a subscript 1. So our continuous time Markov model has 8 states. Okay, with me? And our rate matrix must be 8 by 8. The idea here is that whenever the subscript is 0, you can't change. You cannot change from T to C or T to G or anything like that. When your subscript is 0, you can't change. So, well, how do we parameterize this model? Well, once again, diagonals are easy. We know what to do there. Once we have the off-diagonal parts, we can figure out what the diagonals are. We have a bunch of zeros here. And these are zeros, like, well, let's look at this one. This is a C1 going to an A0. Well, this involves a change in the nucleotide and the subscript in an instant of time. So this is a one event at a time. You can't have changes in the subscript and the nucleotide occurring simultaneously. It's one or the other. So these are 0 for that reason. Then you also have zeros up here, but these are zeros for a different reason. These are zeros because the subscript is 0. You can't have a change in the nucleotide when your subscript is 0. Okay, so those are 0 for a different reason. You have these are rates of change for just the subscript. So this is going from A1 to A0. So this is the rate at which you go from on to off, essentially. And this is the rate at which you go from off to on. Okay. Finally, down here in the lower right, this is a change from T1 to A1, right there, right? This little cell. Subscript's 1, you're good to go in terms of changing your nucleotide. So these are allowable changes in the nucleotide. So the idea here is you put your favorite model there, Jukes Cantor, GTR, whatever. That gets shoved into this little bottom 4x4 part of the matrix. With me? Everything else works the same. Instead of having 4 states, you have 8. All the machinery works just as the same, but there's this one little problem, which is, we all realize you don't see the subscripts, right? You never actually see subscripts, 0s and 1s with your nucleotides. This model, by the way, is called the covariant model, or covariatide-like model of Tuffley and Steele, 97. In terms of the subscripts, we can still calculate likelihoods under this model because it's ambiguity, right? We treat it as ambiguity. Just like when I told you how we initialize the likelihoods when we have a C or a T, right? You just put your conditional probabilities of 1 for C and T. Well, if we see an A, it's like, well, I don't know if that's an A0 or an A1, right? And so if we see an A, we put a 1 in the A0, so this is A0, A0, C0, G0, T0, A1, C1, G1, T1. We put a 1 in both of the slots that would be consistent with A, regardless of which subscript, with the subscript being ambiguous. G, you would put a 1 in the 2 G spots. This is the 1 for the G0. That's a G1. Clear? So this is kind of cool. We actually can calculate likelihoods under a model where rates are varying at that site over the tree, which is pretty kick-ass, I think. I mean, that's pretty interesting, I think. And even though we can't see the subscript, right? Yeah?
What is the 0 and 1?
It's just a way of modeling, so that it's allowing selection to change its course over evolutionary history at a site. That's like the biological thing, or the evolutionary thing that's happening. In terms of, this is just a 2-category model, so if you're interested, what happens with the model I just showed you as the rate of switching. Go back here. As the switching rate, lambda, is the rate at which you switch subscripts. As that rate of switching gets smaller, closer and closer to 0, this model collapses to the proportion of invariable sites model, right? Because it's either on or off, right? For the proportion of invariable sites model, this one allows on-off to switch over the course of time. There's another variant of this model where you have a discretized gamma, so you're allowing it to change into the different discrete gamma categories. You know, if you divide your gamma distribution into 5 categories, then this is going to be the rate matrix is going to be 4 times 5, or 20 by 20, because you'd have each nucleotide would have a label, a subscript for each of the categories, gamma categories it could be in. That was Gaultier, just Gaultier 2003, I think, or 2001. Anyway, these are just models. I mean, it's not like you want to take this too literally. This is, and nobody believes that things happen exactly this way, but we're trying to allow for the possibility that you have high and low rate sites, or that you can change your rate over time at a site. And that's, I think, all I wanted to say. The other stuff I was going to say isn't worth saying. So any questions, and we'll go on to the next bit, which I think is Sebastian. Yes?
We're still under the assumption that what's happening in site A is independent
Mm-hmm.
of what's happening in another site. What if that's not the case?
So if it's not the case, you have to rely on the idea that these methods are robust to violation of their assumptions, okay? And we didn't really talk about the importance of models in biology and how models don't have to be perfect descriptors of the underlying process to be valuable. In fact, if they weren't simplifications, they wouldn't be models and useful, frankly. But this was, a lot of these methods are robust to violations of their assumptions. And there's been at least 2 papers that I can think of that have examined the sensitivity to these methods when you have non-independence. And one was by myself and Rasmus Nielsen in the 1990s. And then Chris Nazaralo, who's a graduate student of mine, and I did simulations under a different type of model, and I'm sure there's others. I just can't think of them. I know my own CV, but I forget some of the other people's CVs. But basic idea is you simulate under a process, simulate DNA sequences under a process where you have non-independent evolution of varying degrees, and you then apply the method which assumes independent, and you see how screwed up it is, right, by violation of its assumptions. And typically one way of thinking about it is when you have non-independent substitution, you actually have fewer data than you think you do. So if you have 1,000 sites and you have a lot of non-independence, then somehow that's equivalent to a much smaller matrix where you have independence, right? That's one way of thinking about it. But, it's not clear to me. I mean, you could still imagine that there'd be systematic weird things that could happen that would screw up estimates in ways that I can't predict. But that's one thing I know is true. It's kind of the equivalent to smaller matrices of independently evolving alignments.